it will have, it is of type list. Now you can turn this into a NumPy array by, so you can turn any Python list into a NumPy array using, by just putting this inside np.array. Let's see what we get. Now we have an object called npr, which if you see the type of it, you will see that it has a type numpy.nd array. Now the difference between the two are as follows. I shall slowly take them one by one. So you can do arithmetic operations with a NumPy array, which you cannot do with a standard library list, which you're using as an array. For example, if you do this, it will give you an error. Whereas if you do npr plus 1, what it is now going to give you is the same array with the number 1 added to each of its elements. So if you add a number to a NumPy array, it does element-wise addition. That is, notice that your npr, so if I print npr, it contains the same amount of data as was there in your standard list array. It contains the same amount of data. Here it appears as a list. Here it appears as an array. If you try to add a number to a list, it gives you an error. If you add a number to an array, it does element-wise addition to the array. So 1 becomes 2, 2 becomes 3, 4 becomes 5, 4 becomes 5, 7 becomes 8, as you can clearly see from here. This is one advantage. The other advantage, the main advantage, is actually computational, which is that most operations that you perform with large data sets with standard library array or std, an array declared like this, it will be quite computationally intensive. This is because it is implemented in Python itself, whereas a NumPy array is implemented with C++ backend. What this means is that when I declare something as a NumPy array like this, it is actually a C++ array that has been exposed to Python. So NumPy as a library has been written in C++. And consequently, Python being a very high-level language, if you remember the first lecture, I had told you that Python is quite slow. It is fast to develop in. It is intuitive, but in computational terms, it is slow. But C++ on the other hand is fast. NumPy is sort of the best of both worlds. So a NumPy array can be operated on with the same speed as you would operate an array on with Python. Now, but there are some disadvantages. For example, we can have, with a standard library array, you don't need all your data types to be the same. So you can have an integer, a float, another float, you can have a string, and then you can have, let's say, another number. If you try to turn this into you will get an array using the same method, but if you examine this array, what you can notice is that this is, of course, yes, this is the array you should examine. You will notice that it has turned every element into a string, and this is because all NumPy arrays have to contain all data types of the same type. So if I were to now do type of NPR of 1, you will notice that it is a string. Now, NPR2 of 1 is actually, it is a number, but it is a number in quotation marks, and it is saved as a string, and it is when you turn it into a NumPy array, it is being kept in the array explicitly as a string. And this is because one of the elements at least have been a string. So the only way that a NumPy array can be created out of this Python list is by turning all elements into strings. So Python does such things which may not be desirable, especially in the case of NumPy arrays. So one needs to be careful about that. So this is about, I would say, one of the only disadvantages of NumPy arrays, which is that it does not allow you to have data types of different types within one array, whereas a list will allow you to have any different types of data within an array. Now, of course, NumPy arrays can be multi-dimensional, etc. So we shall carry out some exercises to understand what that means. For example, I can declare, NumPy has some cool methods to declare arrays. I can do a equals np.zeros of 5, and what I will get is I will get an array, NumPy array of 5 zeros. You can see that this is, of course, you can now, instead of just having 5, you can give it 5, 5. So I should do apparently another bracket. So if I do this now, I have declared a 2-dimensional array in one go of 5 rows, 5 columns, all zeros. Now you can manipulate this as you would with any other array. So a of 2, 4. If you, of course, the second row, 4th column is 0, but you can now declare it to be some other value. And if you do print a again, you see that the second row, 4th column has been modified to have the value of 7. So you can play with an array the same way you play with a variable with these indices, with the first index standing for the row it's in, and the second index standing for the column the values are in. You can examine any array, what type of an array it is, what is its shape, etc., using the parameter shape. So if you print it out, here it tells you it is a 5, 5 array because it has 5 rows, 5 columns. You can, so just like you have zeros, np.zeros, you can also have np.ones. So b equals np.ones of 5, 5. This will give you array of, let's say, a 5 by 5 array of ones. These are just quick ways to, but you can also get, for example, a plus 1. Like I said, if you add an element to an array, you do element-wise. Sorry, if you add a scalar number to an array, you do element-wise addition. So A was all zeros except 7 here, and you have added a +1, so it is now all ones except this one, which is 8. So these are some quick techniques to declare arrays. You also have, you can, for example, declare what you call an identity matrix in mathematics, which is an array in which only your diagonal elements are 1 by doing something called I of 7. Let's try this. So np.I of 7 ident will give you, you see, you get a 7 by 7 identity matrix. So it has 7 rows, 7 columns, only the diagonal elements are 1 and everything else is 0. This is in math what we call an identity matrix, because you can multiply any 7 by 7 matrix with this matrix and it remains the same. So in scalar numbers, the role that the number 1 plays is played in arrays and matrices by the concept of the identity matrix. Now, one of the most powerful features in NumPy is that it has a good pseudo-random generator. So a computer can only generate pseudo-random numbers. It cannot generate what you would call truly random numbers, of course. This is something you should read up on later if you want to understand the nuances of that. But if you want an array with a lot of random numbers for you to play around with, you have the choice of declaring it np.random, let us say 100. So, of course, I made a spelling mistake. That is why it is giving me an error. If I declare this way, now I get an array which has 100 elements in it, and all of those are random numbers between 0 and 1. Now, numpy.random.random has so one of the things you might want to look up is numpy.random. It has, it will only take the size, and yeah, it will always give you a random number between 0 and 1. This is the advantage of the random, but this the submodule random of the library in NumPy contains also other functions. For example, it contains normal, binomial, etc., which will allow you to draw random numbers according to other distributions, not just a uniform distribution. Let us try visualizing these numbers. The first thing we can do is we can try making a histogram of it. So you will notice that I have made, so I have imported matplotlib.pyplot as plt, so I can try making a histogram of it now with plt.hist of array, let's say bins equals 5. And this is now a histogram of the numbers. As if you recall what a histogram is from the first digital Nalanda course, on the y-axis you have bins in which you count how many elements are there of the between those intervals, and on the x-axis you have the bins, and on the y-axis you have the amount of the content in each of those bins. So, for example, what this means is that in this array that I have constructed here, between 0 and 0.2, there are 15 numbers, and between 0.2 and 0.4, there are 24 maybe. This is, I think, 16, not 15, because it's slightly above. So plt.hist is a good way to visualize this. If you want it to have more bins, you can just change the bins parameter, and you'll notice that now there are twice the number of bins. So with 10 bins, the average number per each bin has reduced. So this is a good way to visualize any large array. The histogram quickly gives you a visual feel for what is the kind of data you are looking at, what is the range of the data, etc. Now, you can, of course, also examine the maximum and minimum values of an array without resorting to visual tools by using np.max of this will tell you what is the maximum value in the array, which in this case is 9984. So this is the maximum, the largest value in this array. You also have np.min, which is the smallest value in that array. You can take the sum of all elements in that array using np.sum, and these are all default features that are there in NumPy, which I find quite useful. But the most powerful feature of NumPy in somewhat, let's say, one of the most powerful features of NumPy, in my opinion, is the fact that just like you can do arithmetic operations by adding a scalar in element-wise to an array, you can also do logical operations. So you have this random array which I have just created. Now I can do +1, like I said earlier, and it adds 1 to all the numbers. So you see that it has added 1 to all the numbers. You can also do a logical operation like this. So now you'll notice that it is all false. That is because by definition, the random function returns only values between 0 and 1, as you can see. And so none of those values are larger than 1. So you get an array of the same length as this array, which contains the value element-wise comparison of this. So what is essentially being done is each element is being taken and is being compared against this one using this logical operation. And now you get an array that is that contains the element-wise logical operation results. So you get an array, but all its values are Booleans of either true or false. So here you saw it is all false. You can do rar greater than 0.5. And you will see that some are true now, some are false. This is because, of course, in the array that we created, some values are greater than 0.5, some values are smaller than 0.5. Now, if this was a standard list array and I asked you to pick out all the elements in the list which are greater than 0.5, so let us create a standard list. This is a way to just turn it into a. So this is now a list which contains the same element. Now, if I ask you how to get the values in this that are greater than 0.5, you cannot really. I think this is not a operation that is supported for a list, but it is supported for a NumPy array. So if you wanted to take this list and get all the elements that are smaller, greater than 0.5, you would have to use a loop, for example. You would probably start with the you'll start with an empty list for I in if I greater than 0.5. I, and this is how you would do it. If so, let us examine what is there in. Now this contains all the elements in this list that has the element that is bigger than 0.5. However, in Numpy array, it is very simple. All you need to do is if you do this, you will get. So the same amount of data as in this list has been operated upon, and instead of writing 4 lines and going through a for loop, it has all been done in just 1 line, because this is a Numpy array and Numpy arrays support this. But what you need to understand is that this on its own generates an array, right? Which consists of Boolean values, and any array which consists of Boolean values can be used to index an array. And then what will happen is you will get only the elements where the indexing array values are true. And this is how you end up with this array in this 1 line instead of going through a for. Now you can use, for example, something like let's actually, there should be a different way to do it. Let us try. We can try this. We can examine how long this takes to do. Yeah, okay. We should just to illustrate my point that Numpy arrays are faster, I'm going to do something wherein I import let us examine how long each process takes, just to illustrate my point that one is faster than the other, and that is to do I think you should do process. Let me just examine what needs to be done. So right now I'm Googling what is the correct way to check the time using the time module, because I have forgotten what the function is. Yeah, it is process underscore time. This is how I went. Let us, so now I can do So this tells you how long it took to carry out this operation on an array of length 100. It took about 0.2 milliseconds or about 200 microseconds. Now let us carry this out in a completely different way using the Numpy array and see how long that takes. And well, it appears to be actually taking longer with the Numpy array this time. But if we were to go on, say, 10,000 element long, so this is about, if I were to make a 10,000 long array, now it is far too large to visualize, so it gives you this. You can visualize this, but as you expect, the jaggedness of the distribution has reduced because you're looking at a much larger data set. All these operations work as expected. Now let us try how long this takes. And you see that it is I think this is okay. So in my experience, normally a Numpy array takes less time than a Python list, but maybe process.time is not the way to evaluate that. Perhaps what I should do is okay. Anyway, these are just statements of efficiency when writing code. I'm not 100% sure about why it is giving me larger values with Numpy array than with in my experience, Numpy arrays are always faster than for loops. But it could also be because we are working in a Jupyter notebook, and Jupyter notebooks have other overheads on top of the standard code that is. There are other things that I want you to know. For example, you can declare a multi-dimensional array in Python using something of this form. So so what I have done is I have an numpy.array. Inside that I have 3 lists of numbers. And you can just straight away declare a multi-dimensional array that way. Now, there are multiple ways of accessing the data within a multi-dimensional array. You can do it in this way. For example, so you can just access the rows of this array by indexing it this way. So let us examine what we got in row underscore R1. See, you get just the first row of this array. You can straight away do A of 1, and you get 5, 6, 7, 8. You can, I believe, also do this to get the second column. So yeah, so this now works like a array of arrays, and hence if you give it all 3, it will give you all 3 of the all three of the rows in the array. You can do, I believe, if this doesn't work. Yeah, so you can access the different elements of the sub rows and the sub columns of this array in many different ways, which they are to access, for example, a column. What you do to access a row, you can do this, and to access a column, you can do col equals a of. So notice that these two, the ordering of this is reversed here. If I want to access the column, and for example, if I want to know, I get the second column, so 2, 6, 10. So if you visualize A here, you see it properly as a row by column matrix, and if you want to access just its rows, you can use whichever row you want. The 0 will give you 1, 2, 3, 4. 1 will give you 5, 6, 7, 8. If you use 2 here, you'll get 9, 10, 11, 12. And if on the other hand you want to access the columns this way, you reverse the order of the column and the comma and the number, and you access the columns. You can also you can now do things like sum up elements. Column wise, or you can take what is called a dot product now, if you want. Np dot of row underscore r1 underscore r1. What this gives you is interesting. Of course, because these two elements are these two arrays are of different length, it will not allow you to take a dot product, but you can, for example, take a dot product between two rows. So if you like, and it will give you basically the sum of the row-wise product of two elements. So this is what you're basically seeing is 5 times 9 plus 6 times 10 plus 7 times 11 plus 8 times 12. Basically, standard operations you do with vectors can be done. Np dot. I believe there is also np dot cross. Yes, it will allow you to do row and column cross products if you like. So let us examine how that works. Okay. This does not the cross product features of NumPy do not necessarily translate to how we think of cross products in mathematics. So this you need arrays of the same length, etc. But NumPy has these features which allow you to do full linear algebra with a multi-dimensional array, and these are some of the advantages. Some other things I would like to show you are you can use NumPy to, for example, take row-wise or column-wise addition. So np.sum of A can be done with and you see you get three numbers, and let us examine what those three numbers are. If you print A out, you have a three-dimensional, you have a 4x3 array. So when I pass the element axis to np.sum, it takes the sum along, it takes the sum along these axes. So the first one, 10, is 1 plus 2 plus 3 plus 4. The second one, 26, is 5 plus 6 plus 7 plus 8. The third one is exactly the corresponding one, that's 9 plus 10 plus 11 plus 12. I can now give it, for example, axis 0, and it will give me the row-wise addition, column-wise addition. So now you see there are four numbers which correspond to 1 plus 5 plus 9 is 15, 2 plus 6 plus 2 is 18. So when you take the numpy np.sum and what you're passing it is a two-dimensional array, then you have the option to also tell it which axis along you want the summing to be done. And depending upon the axis you specify, it gives you an array of either the length of the number of columns or the number of rows, and it adds up things row by row. If you do not pass the axis, it will just, I believe, add up all elements in the array. Yes. So these are some of the advantages of using NumPy arrays. In general, when you use code for doing data analysis, NumPy arrays are, in my experience, much faster than Python std library lists to manipulate data with. And NumPy has a powerful set of features for also random number generation. So I already showed you how to generate a large array of numbers uniformly distributed between 0 and 1. If instead you want those to be distributed normally, you can do np.random. I believe normal. So takes, so the first element you have to pass is usually where you want the mean of the normal distribution to be, and that is probably, let's just give it 2. You can also pass what you want the standard deviation of the distribution to be. Let's give it 0.5. And you can also tell it how many elements you want. So let's get 100,000 right now, or 10,000 in this case. And I forgot an equal to sign. This is why it's giving me an error. Now, if I do that, I get ndist, which is a large array. So because it's a large array, it's only showing you the first and the second values. And if you do now np.mean of ndist, which is you're taking the average value of this array, you'll notice that it is very close to 2 because this is where I put the mean of the distribution. If I do variance, I get a value very close to 0.5 square because here what I passed on was the standard deviation, and the standard deviation squared is the variance. And if I do len, I get okay. You shouldn't use np.len, you should just use len. So Python's a standard library operation for length also works efficiently with NumPy. So you can just, so you basically got an array of length 10,000, which has this distribution. Let us visualize this using plt.hist to verify that that is exactly what you got. So and you see a very clean normal distribution with the mean close to exactly 2.0, which is where I mentioned it. Asked the sampler to give it to me. It has given me with a standard deviation of about 0.5, which means that 2 plus or minus 0.5, about 68% of all the elements in the array will be contained in the plus or minus 1 sigma interval. And so this numpy.random.normal allows you to generate such distributions. The fun thing is that if you examine .random this library, it contains a whole bunch of other distributions also. So I only introduced you to normal, which is a Gaussian distribution, but you have a large number of other series that depending upon what field you work in, you will find very useful. For example, uniform is what we got with just numpy.random.random. Yeah, which you can generalize this to have any interval by using uniform, but you can also call any of these functions by looking them up, and you can check at the and it contains all the references to how these numbers are generated, and it is an efficient and elegant way to generate random numbers in Python. The other thing you can do now, since you have generated a distribution, is you can also do array operation between two arrays. So I had earlier showed you that you can add a scalar number. So this now just adds 1 to 1 in an element-wise way, but you can also do element-wise addition of two arrays. So now what you get is you get an array which has the same length as this array and also of this array, because they're the same array and element-wise they have been added. You can do ndist 2, which will give you every number squared. You can do multiplied by 2, which is each number is doubled, etc. So NumPy arrays just work like regular numbers, and you can use them in all mathematical operations that way. And that is an elegant and cool feature of NumPy arrays. Yeah, so this is, I believe that basically all concepts related to what we need to understand with NumPy arrays have been introduced now. So if you have any questions, you can raise your hands and ask me. And I shall try to clear them up right now. If not, we can move on to using. Hi, Modish. I have asked you to unmute. Can you unmute yourself now?
Hello.
Hello, yeah. I can hear you. I can hear you.
Hello, sir. Good afternoon.
Good afternoon.
Sir, I was not able to open the file in on Kaggle. I had worked earlier, so previous file was not able to. I mean, I was not able to access that. So, can you tell me how to save and how to access again that file?
Sure. So,
Yeah.
which file?
I mean, previously we were doing so वो सारा वो पूरा गायब हो गया था सर, फिर वो मेरे को मिला नहीं दोबारा से जो मैंने सेव किया था पहले काम करके.
So, okay. So one of the things that NumPy has is it has the ability to save an array to a file and also open it. So let us now examine, for example, ndist. You can do np.save txt and ndist, I believe. Actually, let us just look this up to be sure we use the correct syntax. So you have to pass it an array and then you have to pass it the name of the file. So let us try test.txt, and you can give it, let us give it this. So now what you have done is we have saved this to a file called test.txt. Since this notebook is living on the cloud, it has saved it somewhere. I let us try opening it now. Open file array equal np.load txt test. Sorry, I have a spelling mistake in what we did. Yeah, so we managed to save this array which we generated here into a file called test.txt, and then we managed to load it back using np.load.txt into another container. And as you can see, you have the whole thing here. This is the simplest form of reading and writing an array in Python. I believe next lecture when I introduce Pandas to you, you will find that much more useful from a point of view of opening and closing files, because Pandas has much better features for let's say formatting data, etc. So is this what you is this the kind of question? Is this what you meant by your question, or?
Yeah, sir, it was it was different, but I was asking जैसे अपने कैगल पे किया है ना सर ये नोटबुक, लेट्स से ऊपर जहाँ पर ड्राफ्ट सेव लिखा हुआ है ना वहाँ पर है नोटबुक 117 ये फाइल है. अगर मैं इसको किसी दूसरे नाम से सेव करता हूँ फिर मैं कैगल में इसी फाइल को कैसे खोलूंगा?
Oh, sure. Okay, let
Yeah.
me try that. Let one. I will save this, right? Maybe it's a bug in Kaggle because it doesn't seem to, Let us just try once more. Okay, it's there. It's just not saving with the what I would think of as the correct name, is it? So I'm now able to access this file by logging into Kaggle again. But you're right, I can't seem to save it as a specific. Oh, maybe I should just. Let's try. Yeah, so I'm able to access this now in, my work on Kaggle. Does this answer your question?
Yes, sir. Yes, sir.
Okay, so
The last lecture on that clustering lecture. So I was missing that.
Sure.
Now it's all. Sir. Thank you.
So yeah, all you need to do is just rename your notebook to something specific, and then you can log in and look at your work, and you'll find those notebooks. So you can run Jupyter notebooks on your computer. You can run it on a cloud, either in Collaboratory or in Kaggle. And the important thing to remember is that depending upon where you run it, the files you save will be on the cloud in that account. And so you need to log in that account with the same account and credentials if you want to access the same file again. But these things should be trivial. I also, but thanks to what Mudish prompted, and not necessarily exactly what he wanted, I showed you some functionality of NumPy that allows you to save an array into a file. This array could be a 2-dimensional array, a 3-dimensional array, all sorts of things, and you will be able to save it onto a file. You can load it back. However, I would actually suggest that if you use Pandas to do a file opening, it's actually Pandas has much nicer features for opening file sets. For example, here I opened this notebook in a Kaggle location where there is a file, and let us try opening that with Pandas. So ptr equals pandas.load _csv. So Pandas is like a more advanced version of NumPy. It is dependent on NumPy for many of its functions, but it gives you an even nicer interface with an array. Let us, for example, this should be better, but of course, I have not. I should do PD because I imported Pandas as PD. So Pandas load CSV. Okay, it should be read CSV, not load CSV. So this is now Pandas is reading a file, and it will read all the data in that file and put it into a what is called a pandas data frame, which is something that contains many NumPy arrays inside it. And so it is in many ways more efficient than, it is more, let us say, easy to use than even NumPy. So now if you examine type of PDR, you see it shows you this is a pandas data frame. You can just print out what is in the pandas data frame this way. So you see that it has many columns. This is like a large NumPy array with 11 columns and more than 6 million rows. You can examine each column. So unlike a NumPy array, a NumPy n-dimensional array in which each data type has to be, each column and each row has to be of the same data type, a pandas n-dimensional array, the different columns can be of different data types. So for example, you can do PD of type, and you see that its data type is an object, but you can also you can access other columns. For example, amount will be just a number, etc. It's a floating point number. So each column, each row in a pandas array can contain different types of, each row cannot be different type of data set from each one, but each column can be a different type of data set from each one. This is actually also possible in NumPy using something called a structured array, but you can look that up. Declaring that is quite a bit more work than just a pandas data frame, which is a much more elegant way. But the way to the thing to understand is that everything you do with a NumPy array can also be done with a pandas data frame rows or columns. So you can look at np.sum, for example, and you see that, you can do min, max, etc. The previous things I showed you, which is you can now make, for example, a histogram of these elements for easy visualization to understand what's going on. And as you see, this is of course quite not intuitive, because the first bin contains almost all the data and the second bin contains much fewer data. So what I'm going to do is I'm going to increase the number of bins, and I'm going to make it a log scale plot. So y scale log. So now if you notice, the y-axis has a log scale, a logarithmic scale, and you can easily visualize the data in 1,000 bits. And there are, like I said, there are like 6 million rows in this data set, and you can visualize it this way. So a pandas data frame contains organized rows and columns. If someone gives you a data set, one of the easiest ways to open it is to just use pandas. It works very much like NumPy in the sense pandas actually uses a NumPy backend, and you can visualize the pandas arrays the same way you visualize NumPy arrays. It is a more convenient front end in the sense that each column can have a name, etc., which you cannot trivially do in NumPy, you can actually do so using something called a structured array. But if you're going to use a structured array in NumPy, you might as well just use Pandas at that point. And yeah, this is what I wanted to show in terms of specific libraries to you for both visualization, which is Matplotlib, and also for linear algebra and so when I mentioned that you can apply cuts in NumPy, in Pandas it's even easier. For example, if you want to find all the transactions in which the amount was less than 1,000, you can do PDR of PDR. Sorry. Less than 1,000, and you will get a smaller array, which now you will notice that here there are only 1.4 million as opposed to the 6 million here. And what has been done is you have taken this column of the 6 million array, you have applied less than 1,000 to it, which then gives you. So just to illustrate what I was saying, let us. You get an array of the same length as your first array, but which contains just true or false, depending upon whether the amount column value is smaller than 1,000 or larger than 1,000. And then if you use this array as an index for the main Pandas data frame, then you get a new array which selects only the transactions which have an amount smaller than 1,000. So these are the advantages of using Pandas instead of NumPy, in the sense that you get all your data in a nicely formatted. You can access each column by just using an index, like it's an index within an array itself. And for all practical purposes, it behaves just like NumPy when you're using it with your visualization library, such as Matplotlib. Matplotlib itself has other features. For example, if you want to plot regular line, like a graph, you can just do plt.plot of, let's say, what the points you want along. So if you do this, what you get is you see each point that is joined by these two lines are the arrays you have passed. So 1, 3, then you get 3, 9, and then you get 5, 25. So you can plot any data series this way. For example, you can plot plt.plot amount versus. This may not turn out to be very useful, but you can plot large arrays against each other. But when you're doing so, maybe better than using lines, it's better to use scatter. This is taking a long time because it's a large array. So instead of using plt.plot, if you use plt.scatter, you just get a collection of the points So if you want the same plot, but without a line joining the different points, then you can use plt.scatter. And it takes a while because it has to go through 6 million data points, right? But it's yeah, you notice that there are, along the x-axis, you have what you pass as your first array, Along the y-axis, you have whatever you pass as your second array. In the next lecture, I think what we're going to do is we are going to use all the libraries that we learned today, which is NumPy, Matplotlib, and Pandas, to analyze a big data set. We will make some occupancy plots. We will classify it. We will look at what are its individual capabilities, etc. In the work session. But for this lecture, I believe we have introduced everything we needed. I will share the notebook with you later today, and in the work session, we will work out some exercises using NumPy, SciPy, and NumPy, Pandas, and Matplotlib on visualizing data sets. Does anyone have any questions? I don't think I should begin a new topic with 15 minutes left. So if anyone has any questions, please raise your hand. Okay, if not, then I think we will stop this class a little early, about 14 minutes earlier than scheduled. In the work session, we will now use these 3 libraries that I have taught you to carry out some exercises. Meanwhile, I would encourage you to go through each of these things that are there inside NumPy, like for example, numpy.random, the different functions that are there to generate samples of data according to different distributions, and use plt.hist to visualize them, and then also use array logical operations, etc., to practice things like cutting on an array, slicing an array, etc. These are fun things to try out. They're extremely easy, and they're quite illustrative, and they are the first step towards analyzing large data sets using Python. So in the next work session and the next lecture, we will actually analyze a big data set using these tools that I have taught you today. Since I do not see anyone raising hands to ask questions, I think I will end this call now. Or at least I'll stop sharing my screen.
Okay, thank you, sir.
Someone had asked, the graph doesn't seem to be normally distributed while the command is random.random. Is this something else? Yeah, that's because when you use random.random, you are sampling a uniform distribution between 0 and 1. If you use random.normal, then you're sampling a normal distribution. So, right. Thank you everyone for attending. The next work session and 2 lectures, we will use the tools that I have introduced you today to play around with big data sets and do some analysis, and in the process, hopefully improve our preliminary skills even better. But just play around with these things. Go to Kaggle, open something using Pandas, and do anything that comes to your mind. And that is really how you become more proficient with these tools. Thanks.